The resources are available, as you know very well, that Dr. Zahid Siddiqui sir. I'm using following that guy. So here in this example we have a 3 meter long column which is short and tight. We have 3 meter long column which is short and tight column, and 3 meter long column. You see here it's tight column. It is also to be it is to be used for the following combination of load. It means there are three different kinds of loads are acting on the column. The column is supposed to support these three kinds of loads. Let's say, I give you an example. Let's say this is a column and it may support one kind of beam here, one kind of support over here, and the other may be on the on this side. Similarly, the case as a column is in, let's say this is our a slab area, for example. If a column is here in the side, the column on the side may have experienced three kinds of loads, three kinds of beams, like one from here, other from here, and the third one from here. Similarly, a column at the corner that experiences two loads, two beams supporting two beams, one from here and other one here. So in this case, our column have three kinds is to support three kinds of combination. These are dead loads and live loads, and moments are given respective. So we have to design a column for to take out these three loads. The column is to be a rectangular section, so it is recommended that the column must be in rectangular section. And other restriction over here is that the one side must at least one side not larger than 375 mm. So the one side of the rectangular section should be restricted to the 375 mm. Let's say this is a rectangular column, you say. So it's one side, either this side or this side, that should be restricted to maximum of 375 mm dimension. Clear? So and the FC prime, the 28 days compressive strength used for this kind of concrete, because this column is 20 megapascal and the aggregate size used is 19 mm. The yield strength of a steel used is 300 megapascal. Now we have to calculate the suitable dimensions and the reinforcement. So the known values, two most important things are the material properties, that is 20 megapascal FC prime and Fy. So first of all, what we do convert all the given loads into the factored loads. You know, in the early when we study the load cases and load combinations, they will see that 1.2 times of dead load and 1.6 times of live load. So similarly, we find here the factor load this one, and for the factored moment we use the same combination and we find the factored moment for the first combination. This was the first combination given to us, where 300 kilonewton 300 kilonewton was the live dead load and 450 kilonewton was the dead load. And similarly there was 58 kilonewton was the live dead, sorry, was the dead moment, and the 1.61 was the live moment. Similarly, on the same basis, we go for the second combination and the third combination, again using the same formula, 1.2 times of dead load plus 1.6 times of the live load. We use find for all the three combination. Here you see that here it is one thing worthy to note that the maximum load is where, which combination is giving or which combination is contributing the maximum load. And you can see here the maximum is 1320 for this third combination, and the load contributed by the second combination is 720 kilonewton meter, and the load contributed by the first combination is 1080. So one thing is sure, so we have to design the thing for the maximum load, and the maximum load acting or contributed toward this column is 1320 kilonewton. So we will be first, if our section satisfied this third combination, then it means it can satisfy the other two combinations as well. So let's move with the third combination. Now we will move with the third combination and we will go for the design. So for this, the first most important thing is, first of all sorry to take the trial trial area of the section. So using the formula that I have described before in the lecture, that there are different formulas for the tight columns and the slender columns in SI unit, in FPS system. So you select the relevant formula. So putting in this formula the relevant values. So you here put the 1320 of the factored load and 13.133.6 as the factored moment, and we multiply with 1000 to convert into the Newton, because previously it is in kilonewton units, so we make it convert into the newtons. So this is FC prime, this value FC prime for 20, and 300 is the FY. So the total area comes to be 14429 millimeters square. So based on this area we can find out a square dimension like 375 into 375 mm. So there is one thing, if you remember, the question covers that it's a rectangular column. You remember that? So question says a rectangular a rectangular column with one dimension maximum to 375. So let's say if we want to make a rectangular column at this level, so we can take one dimension as 375 mm or whatever, and other dimension, this dimension, let's say if we don't take it 375 mm, we take it, let's say 200 mm. Let's say we take this dimension as 200 mm, so the remaining dimension, this dimension would be this area divided by 200, that will give you the this dimension. So we can go further this way. So here in this question, in this example, the writer goes with the 375 mm. So let's get an understanding with this way. But when you are restricted to go for a rectangular column, you can take any dimension at this, that should be less than 375 mm as described in the question. So the other dimension you can find from the area. So it is for 10 mm diameter ties and 25 mm diameter longitudinal bars. We need to find one thing, that is this gamma. Actually, what this gamma means. Actually, this gamma is, let's say this is our this is a you see column, and there are reinforcements here and reinforcement over here. Let's say 3 reinforcement on each side. So the gamma value is actually the distance between these two. Here, this is the distance from here, this center to center distance between these two lines. So how to find this distance? If you know this dimension, yes, if you know this dimension, then you may subtract. Let's say 375 is this dimension. Just an assumption you can make. Let's say this is 375 mm. Then you will subtract 2 times of 40 mm. 40 mm is the concrete cover. This one is the concrete cover here. 40 mm on the both sides. 40 mm from this side and 40 mm from this side. Then is 2 times of the 10. 10 is basically the diameter of the the tie bars. Tie bars also comes outside the main reinforcement, longitudinal reinforcement. So this is the longitudinal reinforcement going up, moving vertically up. So the diameter or the tie bar is on the outer side of this reinforcement. So we subtract one diameter from here and one diameter from this side. So in total we subtract 2 times of the bar diameter, and this is 25. 25 actually this is the diameter of the reinforcement bar, and we want the center to center distance. So center we will subtract half from this row and half from this row. So 12.5 from here and 12.5 of the diameter of the bar from here. So in total it would be 25. And to calculate, this would be the one dimension, this distance here. This would be this distance, that is center to center distance from this bar to the other bar, opposite side bar. And to get the gamma value, we will divide the whole thing with 375, this longer dimension. So this comes to be 0.67. So in this case, when the case is like this, we have to select the one that the nearest value or the lower value, not actually the nearest value, the lower whole value of, let's say 0.67. the lowest whole value of the gamma is 0.60. We take this one, and let's say if we take the value of 77 or like 77, let's say if we take the value of 77, and then if this value comes to be 77, then let's say the lower whole value is 75, then we will take the 75. So we have to check with this stuff with the graphs available, that which graphs are available. Let's say we have a different graphs available, that is point 0.06, sorry, 0.6, 0.75, 0.9. I think we have these three stuff available, 0.6, 0.75 and 0.9 in this book, I think so. So we have to choose this gamma value in accordance to the available graphs. Clear? So next we move. First we we select this one gamma. Now we will find out, either we will check this area of steel, this grass area and this gamma value. We will use these two values to find whether this satisfies the design criteria. Does this satisfy all the three load combinations or not? Just hold a minute. I would like to play the background music for you, and it is actually sorry for interruption. Okay, please. So here we first check for the first combination, and the check is what we find the value of PU over AG. And we know the value of PU, right? And similarly for the value of this one. So here we need to check these values for the from the column interaction diagrams. So in column interaction diagram, hardly I don't have put in the selected slides here, but I will give you the column interaction diagram in separate notes, so you can find there. So column interaction diagram is something like this. This is vertical like square, and there are 3 or 4 curves like this one. This kind of curves, these called the interaction curves, for different values based on the different values of the steel ratio. And to select this column relevant curve, we have to take care of 3 factors. One, gamma value factor, second Fc prime, and third one factor Fc Fy. So based on these 3 factors, we have to select one curve among so many that are available. So once we select the relevant curve, then what we have to do, this axis, along this axis there is the value of Pu, and the value of this value lies on this axis. So what we have to do is, first of all, we need to check so we need to trace the value of this one along this axis. Let's say this value comes to be somewhere here, and secondly, what we have to find, we need to find out the value of the mu over g, this value over here. Let's say it comes somewhere here. So we know we have to move from this line up and from this to right side. So wherever they meet, we need to take that point, we need to note that point, and we need to check either this point is more than 3% or not. We need to check first this one, either this point gives the value of reinforcement or the steel value. That these curves, I tell you one more thing, these curves represents the steel ratios, different steel ratio. These curves represent different steel ratio from minimum 1% to the maximum 3%. But in this question, specifically in this question, the steel ratio becomes greater than 3%. It means it comes to be somewhere here. If let's say this one is the 3% curve, and the value that found somewhere here using this data, it comes somewhere here. If we assume that this curve, and the value for this question specifically, this example, for this value of 7.68 and 3.90, the steel ratio comes to be more than 3%. So we would of course revise the section. So to revise the section, if the given value, if the latest value we are using, it gives you the more than steel ratio more, then it is better, to increase the size, go on the larger side, increase the size of your one dimension of your column. So here it is, we are revising the column size to 375 and 450 mm. So previously this was 375 into 375, now it is 375 into 450. Using again the same concept, we will find the value of gamma. And here 450 minus again 2 times of the clear cover, here then minus 2 times of the steel tie bars diameter, and again the 2 times of the half of the main reinforcement diameter. Alright, so it comes to be equal to 1 diameter and divided by its the total dimension. So here the value comes to be 0.72, and the nearest available curve is approximately 0.75. The nearest whole number comes to be 0.75. So now we will decide based on this factor gamma. Here we again will check for the first combination using the same philosophy. We will be checking the column interaction curve. We will find the column interaction curve based on 0.75, based on fc prime, and based on fy. So based on these three factors, we will again decide which column interaction curve we have to use. So using those for that curve, using these two values, we will find out the location of rho g, where does the value of the steel ratio for this data lies. So here it is using interaction curve that shows that the value is approximately equal to 0.03. I mean it's 3%. It's approximately equal to, but it's not more than 3. So that's a kind of okay. And for second combination, similarly, based on the same phenomena, using the same methodology, we will check for the second combination whether the second combination does also satisfy or not. So again, using the interaction curve, we will find that the steel ratio requirement for the second combination is less than 3%. So that's okay. That's no problem to us. So similarly, we will check for the third combination, and third combination also states that the third combination based on the interaction curve also states that the value of steel ratio required for this also lies below the 3%. So this is also okay. So all the three combination satisfies the maximum value of steel as 3%. So the area of steel that required for our this selected column, if you remember, we have revised the section, we have changed the one dimension. So for this area of steel is 3% multiplied by the area of the gross area of the section. So the area of main steel required for the column section is 5063 millimeters square, and this area is provided by number 10 number 25 bars. 10 number 25 bars can give more than or equal to this area. I clear you? Is it clear? So 10 number 25 bars can produce an area equal to or more than 5063. Now we're going for the ties. So diameter of ties for 25 US bars size bars is the number 10 diameter. So normally we are using here number 10 diameter bars for the reinforced ties. As previously discussed, the diameter of spacing of ties. These are the four options. Either 16 times of diameter of main reinforcement bar, 48 times of diameter of the tie bar, or 375 mm or 300 mm. So minimum of these four would be the spacing between two ties. So that comes to be 300 mm. So here we find the spacing. Now we have to find this spacing is the spacing between ties. from one tie to the another tie. Now we have to find out the also the spacing among the steel bars, the longitudinal reinforcement. There is also some spacing, so we need to find. Let's say uh, I just draw over here. This dimension is 375 mm, and this dimension is 450 mm. So now we have to find how much number of bars we can provide here, and what would be the spacing between these two bars, and if we provide reinforcement in this direction, so what should be the spacing. Let's say this is S1 from here, for the spacing on this side is S1. So S1 is how 375 is the total dimension, then minus 2 times of the clear cover from here and clear cover from this side. Clear? 2 times of clear cover. Then we subtract 2 times of the diameter, of the stirrups or the tie, and again we subtract the diameter of the steel reinforcement, the main longitudinal reinforcement, and we divide it by the 3. Why 3 divided by 3 is because we are going to provide here 3 reinforcements, 3 sections, sorry, in 3 3 spacing we are providing here. So we divide it by 3, so we can get size of one space from one bar to the other bar. That comes to be 83.3 mm, and according to code, this dimension or this spacing should be less than 150 mm. So it is less than 150 mm, so this is quite okay. Similarly, we find the spacing for the other side, and here you see it is divided by 2, not by 3, because we are spacing here, providing here spans are 2. So this is greater than 162.5 mm. I have to check either it should be greater than 162 mm or less than 150 mm. Maybe in previous slide, as I remember, I think it's slide number 11. I guess it's slide number 11 that describes the spacing criteria, how much spacing should be there. You can see the spacing criteria at slide number 11 of the same lecture. So here is its arrangement. You see here we provide 3 for the S1. If you remember, we divide it by 3 because we are supposed to provide 4 reinforcements here and 3 spans. That's why